Hello, everyone. Today I hope to tell you something about primes that you didn't already know. As you might know, prime numbers are those integers which are only divisible by the number one and themselves. Um, one of the one of the things about primes that I'd never heard discussed was the this special thing about twin primes here. The twin prime conjecture is that there are infinitely many, roughly speaking, that there are infinitely many multiples of 6 where the multiple minus 1 is a prime number and the multiple plus 1 is a prime number. Um, we know that there are lots of twin prime positions, lots of pairs of twin primes, but nobody has yet proven that there are an infinite number of these twin prime pairs. But one thing we can do is we can generate the positions which we know do not have twin primes, and by looking at the holes, we can determine where there are twin primes. So here I'm showing the positions which do not have twin primes. For any positive integers x and y, if you plug them into this little formula here, 6 times x times y plus or minus x plus or minus y, multiply all of that by 6, and you'll get a multiple of 6 which does not have twin primes immediately surrounding it. Pardon me. So I'm going to show you a few of them. Okay. So here's a little table here. I hope you can see it. I've got a column for x, a column for y, and then the plus or minus there, that makes 4 combinations. Minus x minus y, minus x plus x minus y, and plus x plus y. So there are 4 forms there. So that's why I have 4 columns for each of those scenarios. So the way we can enumerate these positions is by starting with x and y, just climbing up through the positive integers. Start with 1, 1. That's the first row there, or row 2. And then we can go to 2, 1. And then 2, 2. Then 3, 1. 3, 2. 3, 3. Then we can go to 4, 1. 4, 2. 4, 3. 4, 4. So for each one of those pairs of numbers, we have 4 positions which we know that there aren't twin primes surrounding there. So let's take the first one, for example. 6 times 1 is 6. Minus 1 is 5. Minus 1 is 4. All that times 6 is 24. So then we don't expect to find twin primes surrounding 24. 23 is prime, but then 25 is not prime. So sure enough, it holds. And I won't bore you with the rest of them, but that's the way it goes. So let's take a look for a moment at just that inner factor there. The 6xy minus x minus y, that sort of business there. That's on another sheet that I have here called inner. So if we just look at that inner factor there, and we have the same x's and y's, then we see a bunch of numbers in those 4 columns for the 4 different forms there. And when we find absences, that's where we find twin primes. So for example, if we look there, the first row has 4, 6, 6, 8. Next row has 9, 11, 13, 15. Then 20, 24, 24, 28. They don't seem to be getting much smaller from there. So if we won't expect to find the numbers 1, 2, or 3 a little later on here. So they're missing. So let's think about that. Is that legitimate? Is the number 1 times 6 a twin prime position? Well, yes, it is. 6 is surrounded by 5 and 7, which are both prime. All right. How about 2? I don't see 2 in there. 4, 6, 6, 8. I don't see 2. 2 times 6 is 12. 12 is surrounded by 11, which is prime, and 13, which is prime. Another set of twin primes. Same with 3, that's 18. 17 and 19 are both prime. But then we have 4 here. but we don't see 5. So 5 times 6, well, that's 30. 29 and 31 are both prime. So we can see that everywhere that the twin primes are, there are holes in this enumeration process. So if we think about it that way, the twin prime conjecture that there are infinitely many twin prime sets, positions, is an equivalent conjecture to the conjecture that there is no largest number, let's call it L for largest or last, there's no largest positive integer L such that all positive integers greater than L can be written in one of these 4 forms using two numbers, x and y. Oh, in case that was too complicated for you, what I'm saying is that if the twin prime conjecture was false, that would mean that at some point in this enumeration process, we're able to write every number in one of these 4 columns, given some x and y. So what that seems to indicate is that if it was true, and there weren't infinitely many twin primes, we'd be able to have a mapping after some large number L. We'd have a mapping that every number greater than L could be mapped onto 3 numbers: an x, a y, and a number from 1 through 4, just to designate which of these 4 forms we use to compute it. Either the minus x minus y form, the minus x plus y, the plus minus, or the plus plus. So just 3 numbers would be able to map through this process to provide coverage for every number greater than L. So if you can prove that there is no such largest number L, such that all numbers greater than L can be mapped in this way, then you will have proved the twin prime conjecture. But what does this sort of remind us of? Well, it reminds us of the primes themselves. The primes themselves. Pardon me. The primes pop up where we have holes in a generative process. That's the sieve of Eratosthenes, basically. When we have a prime, then we can cover the ground for it out into the future, and we do that with all of the primes that we know about. And there, where there's holes, those are the new primes. Well, this is kind of a holy ground as well. Here we've got holes in these in this area here, from in these 4 columns here. Well, anyway, we might get into a bit of an idea of constructivism in mathematics, whereas it might be the case that we can't prove that there are infinitely many holes, but whereas we can prove that we can always plug in numbers for x and y and get something out of it, turn something out of it. So it might be one of these cases where if we were to adopt a constructivist sort of attitude towards it, we might run into trouble by trying to describe the holes, whereas we can only describe the things we have, if you know what I mean. Well, anyway, I hope you enjoyed that. Let me know what you think. Maybe you were familiar with this. You can subscribe and share it with anyone that you think might enjoy it, and I'll wish you a pleasant day. Take care.